Great. So thanks for the introduction. I enjoy any opportunity to talk about my research. I am new to the faculty here. I came here about 2 months ago from Stanford University. And I have been working on large and small satellites, most recently on small satellites, but all related to precision instruments or precision engineering, as well as dynamics and control of spacecraft. And mainly focusing on a particular area of application, and that's gravitational science and navigation. So, I'm a new professor. I have only a couple of graduate students, and I'm hoping to expand my research group. So if you're interested in the research that I'm talking about here, please send me an email. Okay, so first the applications. I'm going to see a lot of large satellite missions here. The talk is about measuring position and acceleration and time. And those three things may seem to be unrelated to one another, but in fact, there is a strong relationship between those properties. And I'm going to show you how they're related, and not only in terms of the applications, but also in terms of the hardware one builds to make those measurements. So let's talk about navigation. Here's one that everybody knows, the Global Positioning System. You're probably aware that each of these satellites has its own atomic clock on board to keep precision time. And we perform this navigation not only by getting a precise determination of the position of the satellites, but also that precision clock. So this is a four-dimensional problem that has to be solved. Here's another application, a distributed aperture telescope. Here the idea is, instead of continuing to launch larger and larger mirrors into space, we could use interferometry to launch a series of smaller mirrors, smaller telescopes, and fly them in formation, and then from the data from each individual telescope, reconstruct the equivalent of a large optic in space. And this requires precise information regarding the position of each of these satellites with respect to one another, or in fact, time. So this is the timing of the light waves that are received at each of these telescopes. This is actually an image of a defunct NASA mission called Terrestrial Planet Finder. It was a really wonderful idea, but too expensive, and another mission called Kepler, which you may have heard about, which is a signal telescope, has sort of trumped this in terms of performance versus cost. Another one is geodesy. This is measuring the distribution of mass on the surface of the Earth. And this is done by using satellites to determine or measure the gravitational potential of the Earth, which of course is a result of the distribution of mass over the surface. And this has a lot of implications related to climate change and understanding the Earth system. Here the key, and I'll talk about this a little bit, is measuring acceleration and position. Okay, and I'll explain why. I'll go to this application next. There was a program I worked on for some time at Stanford that used precision gyroscopes to actually measure the curvature of space-time in the vicinity of the Earth. And in this case, the key to making this measurement was understanding the acceleration, or in this case, the angular acceleration of those gyroscopes. Other experiments deal with measuring time in a very precise way. So this was the Gravity Probe B mission. This is a small picture that's representing another mission called Gravity Probe A, where it looked at the difference between a precision clock on the ground and a precision clock on a satellite. And as it traversed the Earth's gravity well, there was a frequency shift between those two clocks that's predicted by general relativity. And this to this day is one of the most precise measurements of this gravitational redshift, as it's called, of light. And also position. So this is a schematic drawing of measurement of the bending of light rays as they traverse or come close to a massive body. So fundamental physics can look at position, acceleration, and time, or any combination of these. The last one, and the one that I am working on sort of in my other hand, small satellites in this hand, and this one, gravitational wave detection in the other, is really the grand challenge in terms of accelerometry and position measurement between multiple spacecraft. And I'll leave it at that because I'm going to talk about it a bit more in a second, or in a few minutes. So I'm going to first talk about precision clocks and metrology, or distance measurement, or position measurement, because these two measurements are often interrelated and interchangeable. One piece of equipment that we use is an atomic clock, which is not a new technology, but continues to improve. But more importantly for this group, it continues to shrink down in size and power. And we'll talk about how we can actually, I have a proposal out now to look at using a precision atomic clock on a CubeSat. And I'll talk about that in the next couple of slides. Basically, I like to get across the fundamental point about how these work without going into all the details. Basically, the idea is you lock the frequency of an electromagnetic wave, and that could be optical frequencies or it could be microwave frequencies, to a hyperfine transition of an element or a molecule. So the electrons in the outer shell of an atom, say, are classified by specific quanta of energy, and these are fixed and known, and because of that, the certain molecules absorb light at certain frequencies better than other frequencies, and you can actually use that as a measurement and a feedback mechanism to lock the frequency of your light source to that atomic transition. And that is actually a true clock. In other words, what do I mean by that? It is locked to a very specific frequency. It's a fundamental frequency of nature, let's say, that doesn't change over time. And that is to be compared with an optical clock. Here the idea is you have a cavity, so say two mirrors, and you're bouncing a light beam between these two mirrors, and you're adjusting the frequency of your light source so that there's a resonance between those two end mirrors. And if the length is fixed, then your frequency is fixed. However, if that length changes, the frequency you measure changes. And therefore, an optical clock and optical cavity can measure time or length, which is the same as position, but not both. You're essentially getting one or the other. So this is one way that time and position are interrelated. The third important instrument is an interferometer. This is a technology that's now 100 years old, although laser interferometry is about only half as old as that. And this is the basic idea is to use constructive and destructive interference of electromagnetic wave. And typically, to get the high precision, you want to compare two length scales. You're comparing one length with respect to the other. So if you have one, we say a reference arm of the interferometer that's fixed, and then the other arm is changing, you're actually measuring the change in length of that other arm. But you can't measure both absolutely. You're only measuring one length with respect to another. This is just a precursor for what I'm going to talk about here. And I told you that I wanted to keep the concepts simple so that you could understand the basic principle of how the instruments works. But when you get down to all the details and getting the best performance and best frequency stability you possibly can, you end up with a setup like this. This was one of my labs at Stanford. And I won't go into too much detail, although here is a laser you can barely see that runs through this chain. It's actually an infrared light that eventually gets converted into green light in the exact same way that my laser pointer is converted into green, and then brought through this plastic tube here. And this actually has molecular iodine, so I2 gas inside this. And there's a feedback control mechanism that there's actually an optical clock. You can't see it, but here are two boxes, and inside those are two optical cavities. And you're reading the frequencies of those two cavities with respect to one another. And there's a lot of science that can be done with this by comparing one clock with respect to the other. And eventually we hope to bring the size of this, this is probably 16 by 4 in the laboratory feet, down to a scale where we can actually fly some of these technologies on a small satellite and do some new and interesting physics experiments. Okay, so now I talked about precision time. Let me talk a little bit about something else called time transfer. This is something that GPS does all the time. We have one atomic clock, and we think it's the best atomic clock in the world. How do we know that? How do we know what the performance of that clock is? The only way you can know is actually to compare it with another identical clock. And looking at the differences between those two clocks, you can get an estimate of what the performance is. So then the question is, if I want to put a very precise clock in space and say there's only one clock on that satellite, how do I know what the performance of that clock is? Well, what we'd really like to do is compare the time associated with the clock in space to one of your ultra-precise clocks on the ground, and use that as a method of determining its performance. And so that's one application of time transfer where you're actually using it as a performance metric. The GPS system uses time transfer to tell us where we are on the Earth. And there's also a whole host of other science, gravitational science and physics experiments that can be done by having the ability to compare the clock on the ground to one in space. And here's a picture of this laser ranging system near Goddard Space Flight Center in Maryland. You can't quite see it, but there's a laser pulse here. This is the moon. I don't think it's actually trying to go to the moon, but what they're actually doing here is comparing a clock on the ground in Maryland to the clock on board the Lunar Reconnaissance Orbiter. And that clock is used to do laser altimetry on the surface of the moon. And this is a demonstration of time transfer to that vehicle. And the way it's done is simply by shooting light pulses, so short pulses of light from the ground to space. And if you know the exact time of flight, so you know the distance between the ground and the satellite, you can calculate how long it will take for that pulse to get there. And then you compare the arrival time of that pulse with the onboard clock. And you do this many, many times, you can get a comparison between the two clocks. And once again, the devil is in the details here, because there are sort of several other things that we need to account for to be able to do this accurately. Of course, we need to know the satellite position to get the range. We also need to know the satellite attitude, because even attitude changes can affect the position of the location of where the light pulse is received with respect to the clock, okay, because those are not co-located instruments. There's atmospheric effects, and there's actually also relativistic effects that must be accounted for. And I think I will leave that there. And so this is something I'm quite excited about working on, maybe starting next year. And maybe some people in this room might be interested in working on this project. And this is demonstration of precision time transfer with a CubeSat. And here the idea is you have a 1U CubeSat. So I presume people know what CubeSats are in the small satellite level. Okay, so one CubeSat, and in it would be one of these clocks. So this is a chip-scale atomic clock by a company called Metrology. There was actually several companies competing to win an award from the Army to design one of these very small clocks. And this company here, Metrology, actually commercialized their product, and it's for sale, although you need to wait 6 months to get one. But anyway, you can see sort of the scale of it. Here's a quarter. It consumes about 160 milliwatts of power, certainly enough power on one CubeSat to power this clock. So you have this clock on orbit, and you want to compare it to a clock that's sitting on the Earth. Well, how do you do that? So the idea is to have a laser terminal on the ground, either one of these commercial laser ranging facilities, or perhaps even building our own laser facility here at the University of Florida, and sending the light pulse up to the satellite. We have photodetectors that clock the arrival time of that light pulse, T1, with respect to the CubeSat clock. And at the same time, there's a retroreflector that returns that light pulse back to the Earth immediately. And the return signal is recorded by another detector on the ground, T2. So what the expectation is, if you look at the emitted time T0 and the received time T1, the average of those two times is the time you would expect the light pulse to have arrived, because there's one-way travel and the return travel should be the same. Okay, so by taking these two measurements, plus this measurement on the satellite and comparing it with the clock, and then you transmit that, T1 minus T cubed, basically just using the regular communications link, we're able to reconstruct this sort of this simple expression here to calculate chi, which is the timing discrepancy between this clock and that clock. Okay, and then there's this other term delta here, which captures all of these other effects that we need to worry about. And again, there's a lot of details in this. One thing, so as another check of the performance, there will also be a GPS receiver to get GPS time and compare that with the CSAC time. The GPS clocks, I believe, are a bit better, but not orders of magnitude better than this clock, and also position information. Okay. So let me go on to, I'm going to sort of change topics. That was something relatively new that I began working on since I've been here at Florida. Now I'm going to talk a bit about what I've been doing basically for the past year while at Stanford, but still here at Florida. And it's related to something called drag-free. And let me explain what this is. So first let me introduce this by saying, okay, the main goal here is now measuring acceleration. And I'm going to talk about two aspects of it. One is measurement of acceleration, and the other one is compensation. Okay, in both cases, the goal is actually to measure something called geodesics. This is a physicist's lingo for a purely Keplerian orbit. So a geodesic is the path that a particle traverses in space-time if there are no external forces applied to it. So it's just dominated by gravity alone. So the idea here is to measure these geodesics and how they vary both in space and time. And by doing this, we can learn something about the gravity field of the Earth. We can learn something about the gravity field of the Moon. There's a mission called Grail around the Moon that's doing a similar technique. And we can even do some pretty cool astrophysics with this technology as well. So you'll know what an accelerometer is. It's basically a device, so you have some mass, in here, which we call test mass. It's connected to a satellite with basically a set of springs. And then the most precise version of these springs are actually electrostatic springs. And the idea is, you think about it as a device for measuring the acceleration of the satellite, but what I really want you to think about it is a device for measuring all of the gravitational forces acting on a satellite, right? Because if this accelerometer reads exactly 0, then we know that the satellite is in pure free fall. So we measure the position of the test mass inside the satellite, and by knowing these spring constants, we can back out what the acceleration is, or what the external forces acting on the satellite are. Okay, so now this is to be compared with something else called a drag-free system, where you eliminate those springs altogether. And so now you have two bodies. One is a test mass. It's shielded inside the satellite. And you measure the position of the spacecraft with respect to the test mass. And because it's completely surrounded, there are no external forces that can be applied directly to the test mass. And therefore, the test mass is following this pure geodesic. And through a feedback control system, with propulsion on board the spacecraft, you have the satellite chase that test mass along its pure geodesic. Okay, so it's sort of a formation flying, but you're flying in formation with this object that's shielded inside the satellite. And there's a trade-off between these two approaches. The drag-free system tends to be much more accurate, and that is because you're canceling those forces from the very beginning, instead of an accelerometer, which tends to try to determine very small forces on a satellite that's sitting on top of a large drag force or some other external forces. So it's a problem of dynamic range. In other words, you're measuring atmospheric drag, which is 10 to the minus 7 g, but you need to get a measurement that's 10 to the minus 11 g. So you need an accelerometer that is good to 1 part in 10,000. That's difficult. With a drag-free system, you're canceling the drag from the beginning, and so you don't have this part in 10,000 issue. Of course, the downside is you need fuel to fly drag-free, and therefore there are lifetime limitations. Here is a brief history of drag-free technology. The very first drag-free spacecraft, which is pictured here, is called Triad 1. This is a pre-GPS navigation satellite. So the idea is you have the satellite flying drag-free, and the motivation here is in orbit determination. The most difficult part of determining and predicting a satellite's orbit in the future is the uncertainty associated with atmospheric drag and solar radiation pressure. So if you cancel those two forces out with the drag-free system, then you have this autonomous satellite that's following this much farther in the future exactly when and where that satellite is going to be. And this allowed the US Navy, who was using this satellite to track ocean-going vessels, to basically ignore it for a month or more than a month, and then be able to talk to it again and know exactly where it was. Whereas previously you had to update the ephemeris once a week or maybe even more. Here's another satellite that's near and dear to my heart. This is Gravity Probe B, launched in 2004. This is the precision gyroscope experiment. I don't have too much time to go into details, but the idea was to look at the drift in a set of very precise gyroscopes to measure some predictions of general relativity. And we, in fact, did that. We published the results of this experiment a little over 1 year ago. And it flew drag-free because it needed a drag-free system to eliminate or reduce the suspension forces that hold that gyroscope inside its housing. Without it, the classical torques on the gyroscope would have been too large for us to be able to measure the relativistic effects that we wanted to measure. Here's another mission that you may have heard about called GRACE. It's not drag-free, but instead it has precision accelerometers. So here I mentioned in the beginning, measuring the Earth's gravitational field, and how we do it. We're interested in measuring acceleration and position, and that's exactly what this formation of two satellites does. So each satellite has its own precise accelerometer that measures all of the atmospheric and other forces acting on the satellite, so that if you, by analysis on the ground, measure what those forces are, you can subtract them out and then reconstruct what the orbit would have been if there were no atmospheric forces. And then you can learn what the purely gravitational orbit would be, and therefore you can learn about the mass distribution on the Earth. But in fact, that's not good enough. To make the measurement accurate enough, what you really want to do is have two satellites, both with accelerometers on board, and instead of tracking its position, you measure its position with respect to the other satellite. And this is a gravity gradiometer, essentially. You're measuring the gravity gradient across these two satellites. And the reason you want to do this in a sort of differential measurement is because you can measure this distance down to micrometers, whereas the knowledge of a satellite's position, a regular satellite's position, is typically good to a meter, maybe 10 centimeters with GPS, and that's not good enough. And finally, LISA is a gravitational wave observatory, 3 drag-free spacecraft now, and so it's similar to this, but you have a third spacecraft. And the reason you do this is to cancel out some uncertainties in the onboard clock. I won't go into details of it, but basically the idea, if you know a laser interferometer has 2 arms, and you're making this differential measurement, and the reason you do that is because the laser has a frequency instability associated with it. But if the 2 arms of the interferometer are the same length, then as those photons traverse the arm and come back, the noise associated with the laser will be the same, and they cancel one another. So this is LISA, which is a laser interferometer space antenna. So now we're using interferometry to measure the distance between satellites, not around the Earth, but actually flying around the sun. And they're all drag-free. And instead of measuring micrometers, now we're measuring picometers. So this is 1 million times more accurate than this. And if we can do this, and we will probably in 10 or 15 years, then we can open up a new way of observing the universe through the gravitational wave spectrum. And so this is one of the main things I'm working on, as I said, in my other arm. Okay. So here I talked about a few of the applications here. I'm showing them again. But here I want to plot them in terms of how well do you need to measure or cancel the acceleration, and on the other hand, how well do you need to do the position measurement, the metrology. And Grace is here at the top, as I said, micrometers, and sort of 0.1 nano-G here. So 10 to the minus 10 G, this is meters per second squared. Gravity probe B was a bit better than that. There's some tests of fundamental physics that need even further improvements. And down here, the ultimate goal is this gravity wave observatory, where, as I said, we need to make this factor of 1 million improvement, both in terms of the measurement of the external forces, which is the drag-free part, and through the laser interferometry. So that, in a nutshell, is sort of the sorts of projects that I'm working on. Now I'm going to go through and show you a few slides of some of the specific things I'm working on in terms of technology and mission design, and actually building and trying to fly some of these technologies on small satellites. One is this instrument that we've been developing at Stanford since probably about 2006, called a gravitational reference sensor. Here is essentially an instrument for a drag-free satellite. You have a test mass, you have some optical equipment here. So this is a shadow sensor that I'll talk about in a moment. But this is basically a sensor to measure the position of this test mass with respect to the spacecraft. Another key ingredient is an ultraviolet light source, and I'll talk about why we need that in a moment. So as I said, the idea of a drag-free system is to cancel out all of the external forces acting on the proof mass, or the test mass, but you can't do that perfectly well. There's always going to be some residual forces acting on a test mass, and the question is, how low can you reduce those residual forces and get the performance that you need? And so this turns out to be sort of multidisciplinary optimization problem, there are about 30 known noise sources or sources of force acting on the test mass. And most of them actually come from the spacecraft itself. The spacecraft produces electromagnetic fields. Those interact with the test mass and push on it. There's not a perfect vacuum inside of this housing, so there are some residual molecules that impact the surface and nudge it a little bit. In fact, the photons from these position sensors are actually enough to swamp the measurement you're trying to make by a factor of 1,000 or so. So you have to be very careful even about the photons that are using to detect the position of this test mass. Okay, so here is one of my goals in say 5 years is to fly now a 3U CubeSat drag-free. And this is something that has never been done. Typically, typical drag-free satellite has been maybe 100 kilograms or hundreds of kilograms and hundreds of watts. So I'm trying to do this with a couple kilograms and a couple watts. And there's a whole host of reasons why you would want to do this, even beyond just reducing cost and reducing the time to flight. There's actually a lot of interesting science you can do if you have a constellation of these low-cost drag-free satellites. And here the goal is to achieve this 10 to minus 12 meters per second squared per root hertz, and the goal here is for Earth geodesy. So that's sort of a performance goal. I don't know if we will achieve that, but that's what we strive for. So there's this gravitational reference sensor, which is just a housing with a spherical test mass inside. There's a motor and gearbox that is what we call the caging mechanism, and this grabs onto the test mass during launch because there's a very harsh environment. This is about 170 grams, and these distances are about a little over a centimeter. And if you were just to let that go, it would completely destroy the satellite during launch. So you have to hold onto it very tightly during launch, and then once you're in orbit, you have to very gently let it go and initialize your control system to put the satellite into a stable drag-free control. These holes are for the optical detection that I'll talk about in a second. There's a standard flight computer electric power system. There's a single thruster on the back, and we're probably going to replace this one, but this is actually a cold gas thruster developed by a company called VACO. There are actually some electric propulsion systems that are becoming available in the next few years that way outperform this thruster. And then in the front here we have a attitude determination and control system, and this keeps the satellite pointed in the right direction. And I'll explain in a second. So I'm basically one chart talking about each of these systems on board the satellite. How am I doing on time?
About 6:55.
Okay. I alluded to the fact that we needed ultraviolet light inside, and why is that? Well, we have this test mass. It's freely floating inside the housing, and because it's not touching, it's perfectly isolated, and it can differentially build up electric charge with respect to the satellite. And if the potential difference between the satellite and the test mass gets too large, then large forces are built up between the two, which just ruins the performance of your system. But at the same time, that can actually do damage if there's arcing and other horrible things that go on. So you need a way of controlling the electric charge, or you think about it as the voltage of the test mass with respect to the voltage of the housing. And you have to do it without touching it, right, or without disturbing it. So the idea here is to use ultraviolet photo emission, and this has been done on Gravity Probe B. The idea is if you shine ultraviolet light on the proof mass, and the work function on the surface of the proof mass is just right, you will pick electrons off of the surface. And then additionally, if you bias the voltage of an electrode that surrounds this light source, you can get these electrons that come off the surface either to go towards the big, bulky mercury lamps that are shown here, the sort of tens of kilograms and tens of watts, would never work on a CubeSat. And just like you are now doing with your holiday lights, we can replace this whole system with some LEDs. And this LEDs emitting in the ultraviolet have only been around for maybe 7 years and never flown in space. Now we are working on trying to actually demonstrate this technology for satellite charge control, not only for this drag-free CubeSat, but for any other application where you have parts of the satellite that need to be electrically isolated and can potentially build up charge with respect to one another. The other nice thing about this is you can actually do it in AC as opposed to DC. So you're modulating this bias very rapidly and modulating the light of the LED very rapidly. And depending on whether that modulation is in phase or out of phase, you can charge up the proof mass or charge down the proof mass. And that's actually a very powerful thing. So let's see, in September of 2013, we are actually going to demonstrate charge control using these ultraviolet LEDs in space on a satellite built by the Kingdom of Saudi Arabia, which is an interesting collaboration. So this is the payload. It's a small satellite, but not a CubeSat. The payload is about this big. The satellite is probably twice as big as that. We have an electrically isolated proof mass. We have a series of actually 16 of these LEDs because we want to get an idea of, we want a distribution of performance and possible failures due to the orbit environment. So we fly many of them so we can get some good statistics on the performance. And this is a collaboration between myself and people at Stanford, the NASA Ames Research Center, and Saudi Arabia. The other technology is this optical detection. This is actually a thesis of a student at Stanford all by itself. The idea here is to measure the position of this test mass with respect to the housing, and you want to do that at the nanometer level, which is not trivial, but you also need to do it in such a way that you're applying less than 10 to the minus 12 meters per second squared of acceleration on the proof mass. So this is done with a series of emitter and detector pairs, and they're set up in such a way that they have two advantages. One, the measurement is a differential measurement. So let's see, so here's detector 3 and detector 1. So if we look at the difference between the output of detector 1 and detector 3, that gives us the delta x position. Because as it moves this way, more of this light is occulted by the sphere, and less of this light is occulted, and that gives us a position measurement. In fact, a very accurate position measurement, because it's insensitive to variations in the intensity of the emitters, because it's differential. So all the emitters are connected together so that if the intensity of light varies slightly, you don't see it in the measurement because you're subtracting it out when you do this subtraction. And then the second advantage is that you can arrange them in such a way that all of the optical power on the test mass cancels one another out, and you can achieve this this noise requirement. And this is some measurements that were made now a couple of years ago with this instrument in the lab, about a factor of 30 below this 1 nanometer sensitivity goal. But that's actually mainly due to the poor environment in the laboratory and would likely be much better in space. And so there's a CubeSat mission that I'm working on. This here is a 3U, again, to demonstrate this sensing system that I talked about, but also to look at some of the attitude and orbit determination hardware and analysis that is required for the drag-free CubeSat. Propulsion is another issue. I don't really have time to go into it. There are a couple, let's say 1 or 2 off-the-shelf thrusters that are sort of CubeSat compatible, but there are many more that will be available and even have higher performance in terms of thrust noise in the next few years. And then another, something that I really enjoy doing is the control design. So here's the control system, or at least a sketch of a control system for the drag-free CubeSat. I don't think I'll go into all the details except maybe point out the main features. So one way to do drag-free control is to have thrusters on all sides of the satellite so that you can use that to nudge the satellite in any direction you want. It turns out, of course, that uses 6 times more fuel than if you have just a single thruster. So here the idea is you have just one thruster in the back of the satellite that pushes against the atmospheric drag. And then to handle the transverse forces acting on the satellite, you use attitude control. So here's the satellite flying this way. If there's a force in this direction, you adjust the attitude slightly that way so that when you fire your thruster forward, you compensate for those lateral forces. And so there's an inner and outer loop control where the inner loop is operating at a higher frequency and is doing this attitude control with a reaction wheel system, and then a slower outer loop drag-free control. And it's been demonstrated to be stable with hardware that is already available for people building CubeSats. And this is my last slide. The main point I want to make is that I have a couple of really interesting CubeSat and nanosatellite projects. I'm looking for graduate students. I even have some funding. And I think there are opportunities both at the master's and PhD, but also at the undergraduate level to contribute to this work. And again, send me an email if you are interested. Thanks. Questions? Yeah.
What kind of processing power do you need to handle all these things? If you're looking at such, if you're trying to balance having the cage system inside, would you need a fairly high frequency processor to handle all that?
Let's see. Not really, actually. This design for this is assuming. I don't know if you're familiar with the Texas Instruments MSP430 processor. The way to get all of this done is to have multiple processors. So the flight computer doing this drag-free control. And these, I said high and low frequencies, but in fact, the inner loop operates at around 10 hertz, and the outer loop is sort of 1 hertz. So it's not really that fast. But the sensing, for example, that optical sensing, does some interesting optical tricks to get this 1 nanometer sensitivity, and that actually requires some fast computation, so it needs its own processor. So by having a couple different processors, we can get it to all work. The question that we're asking and may have problems with is do we have enough power to support the processing need and everything else we need?
Would deployables make it difficult to use the thrusters? And
that's right. Deploys make it difficult to use the thrusters, but also remember, we're trying to fly, ideally we'd like to fly the satellite in formation with a test mass sort of at the micrometer level, so that the satellite is fixed with respect to the test mass down to micrometers. So if you have deployable arrays, they can flex and bend and vibrate, and so vibration as a disturbance is probably a bigger issue. So either body fixed only, and if we can't get away with that, then deployables, but somehow design them in such a way that they are stiff enough that they don't cause disturbances. Other questions? Okay, well, thanks again for your time, and thanks for inviting me.